Okay, good day. This is AP Calculus. I am Mr. McCully, and this is the presentation for section 8.2, integration by parts. This is kind of a bonus section, so let's get right into it. So today's goal, we're going to find an antiderivative by using integration by parts. Now, what is integration by parts? Well, integration by parts is useful for integrating functions that are composed of products of transcendental functions. It is also based on the product rule. So this is a general product rule. So if I take the derivative with respect to x of u times v, that's you're going to leave the first one alone. The derivative of v is dv over dx. Then you're going to leave the second one alone and take the derivative of u, du over dx. And so the um, the integral of the left-hand side should be the original. So uv would be the integral, and since we can separate the integrals of a sum by integrating each of the terms in the sum, we can take the integral of u dv over dx plus the integral of v du over dx. The x's cancel, so you've got uv equals the integral of u dv plus the integral of dvu. And so what we can do is we can bring this integral of v du over to the left through a subtraction, and we can say that this integral u dv right here is equal to uv from right there, subtract v du, and I have a little thing on the side. Let's get rid of that. Okay. All right, so let's move on. So guidelines for using integration by parts, and this is what's really important here. So when you are trying to make a decision on how to integrate by parts, you say, all right, let dv be the more complicated portion of the integrand that can be integrated. So you're looking for something that you can integrate. Let u be the portion of the integrand whose derivative is simpler than u. So when you do the derivative of u, you want something that's going to be simpler than the original one. Sometimes that doesn't happen, especially like as for instance, if you have a composition of two functions, you might get something where you have to do, when you do the derivative, you get an additional term, and so you want to stay away from that. Also note that dv will also contain the dx from the original function. So let's take a look at a first example here. And that first example is the integral of x to the fourth times ln x. And here again, we have our product. So why is this a good candidate for integration by parts? Ln x is a transcendental function, and it doesn't have a nice integral. We don't have a nice integral for the integral of ln x. But it's easily derived, and 1 over x is simpler than ln x because we can write that as an exponential, x to the negative 1 power. And x to the fourth is easily integrated. So what we should do in this particular instance is we should say, okay, I am going to let u be the ln of x. And then I'm going to come down here, I'm going to say dv is equal to x to the fourth dx. All right. And so now we know that the derivative of u, this is going to be du, will be 1 over x dx. And then we can integrate this one, and since it's simple for us to do, we can kind of do it in our head, and we can say that v is going to be 1/5 x to the fifth. Now, yeah, we're going to put a c in there, but we got to go back and do an integral anyway. So we'll save that c for the end. When we're done, we'll put a little c on the end and say, okay, done. All right. So now that I have all of these pieces, the easy derivative of u, the easy integral of dv, I can come down here using the, excuse me, the integral, darn it, the integral of v du is equal to, oops, I did that backwards, sorry. The integral, let's just look, make sure I do it right. So integral of u dv equals v du, okay, we got it. So the integral of u dv is equal to uv minus the integral of v du. All right, so now again, why is that important? Well, if we say that this is the integral, the uv, that's already done. We don't have to worry about that integral. So we're just going to go u is ln x, we'll leave that alone, and then we're going to multiply that by v, which is 1/5 x to the fifth minus the integral of v 1/5 x to the fifth times du. Now, oops, that's v. Don't put an extra. V, or excuse me, du is this 1 over x dx. So I'm just going to put that in there, 1 over x dx. And by doing this, we can simplify this, and then it becomes a fairly simple integral. I can say that this is the ln of x times 1/5 x to the fifth. I'll bring this fifth out, so it's minus 1/5. And then x to the fifth over x is the integral of x to the fourth dx. And that's a simple integral. And so combining a few things here, let's see here, I'll have x to the fifth ln x over 5 minus 1/5, and then we've already done the integral of x to the fourth dx. That's once again 1 over 5 x to the fifth. Since we're done integrating, we'll throw in that extra c, and then we could probably simplify that a little bit more and say it's x ln x over 5 minus x to the fifth over 25 plus c. Yeah, I like that. That's good enough. All right, not bad. So let's continue this, and let's talk about when you should use the integration by parts and when you should use just the simple substitution, because in the homework they throw all kinds of them at you, and some of them it might be easier to do an older method of integration than necessarily doing it by integral by parts. So let's look at this first one here. And so first off, let's make it this. Let's talk about this one. We've got the integral of x squared times e to the x to the third, and there should be a dx there, so put that in your notes. And the integral of x sine x dx. And so one of these is probably best solved by integration by parts, and one of them is probably best solved by some other method. So if you're stuck, like on a standardized test, and you don't know which one to use, well, the best way to do is look at the more complex part. So in this one right here, and I'm just, you know what, I'm going to type because it might, my handwriting, because I'm going to do a little bit here. Clearly, we have the product of a transcendental function, Transcendental. No? Thank goodness for squiggly lines. Transcendental function, product with another function. And so we think, okay, maybe this is going to be integration by parts. But if I look at this higher function, this bigger function, and I talk about e to the x to the third, this is clearly the more complex part. All right. But when I do the derivative of this, if I say, let's take the derivative of this thing, I get e to the x to the third times 3x squared. And I should have a du here, or dx there too. Screwed that up. Did I do that on both? Yeah, I probably just cut and pasted them. No biggie. All right, stay on target. Stay focused there, Macaulay. So at this point, I see, hey, I got 3x squared. I've got an x squared there. So I can make a substitution and say let u equal 2x to the third, and then du equals 3x squared dx. And when I do that, I can come down here and I can say, all right, I'm going to put a third there. I'm going to put an integral. I'm going to reorder this and say that this is ex to the third. And then I bring that 3 from the top over here, 3x squared dx. And so now this is an integration by substitution, and say it's 1/3 integral e to the u du. Just do a substitution. There's my du. I have it right there. There's my u. And now this is a simple integration. It's just 1/3 e to the u plus some constant c, which we'll rewrite as a final answer of 1/3 e to the x to the third plus some constant c. And we didn't have to go through that whole process. Now, could you have done this integration by parts? Absolutely you could, but it would have been a more challenging task than doing it with a substitution. All right, what about the second one? What about x sine x? All right, well, let's talk about this. And again, we clearly have a product. This is a product of a transcendental. All right, and I still can't spell it correctly. We'll get there eventually though, transcendental. All right, and sine x is more complex. More R-E-C-O-M-P-L-E-X, period. All right, but sine is not a composition of two functions. Or at least sine x is not a. Sine x, not a. Get with it. All right. So let's say, as a for instance, we take the derivative of this thing and say that x is u. We get d over dx of sine x. Well, that's just cosine x. All right. If we take the derivative of that. And so let's say we choose, and again, we see this isn't going, I don't have a nice easy substitution to deal with this extra x like I did here. I had this nice derivative portion that I could make part of the change from dx to du. I had that portion and I could do that nice easy substitution. But when I do the derivative of sine x, I get cosine x, and I don't get that extra x. It doesn't help me a whole lot. All right, so let's make an attempt. All right, obviously this is the more complex part. So let's say I say u is equal to sine x, and that v is, or excuse me, dv is equal to x dx, kind of like what I did in the last one. All right, well, this isn't still an easy derivative. Du becomes cosine x dx, and the integral gives me v of a half x. And again, it would be, if we did the integral, we'd say plus c, but we're not even close to being done yet, so we'll save that c to the end. And I can do the same thing. I can set it back up. I can say that the integral of u dv is equal to uv minus the integral of v du. Now what happens though when I do this particular setup, well, I can do that. I got my half x, and this should be squared. Half x squared is the integral there. Sorry about that. Times the cosine of x minus the integral of v half x squared, and then du would be cosine x dx. Now when I look at that thing, I go, whoa, wait a second. This one here is more complex than my original. That didn't help me a whole lot. All right, that didn't, in fact, it doesn't help me at all. So what do? Well, we make another attempt is what we do. We say, all right, that didn't work. Let's change it up. let's change it up. Let's say u is x, and then du would just be dx. That's simpler. I like that. That's going to make my du is just going to be dx, whatever that is. And then if I make dv sine x dx, well, the integral of sine x we know is negative cosine x. No, it's cosine. Yeah, negative cosine x. All right, so now let's try that substitution. Same thing. I haven't changed this part. I just changed the order. So now I can go x times negative cosine x minus the integral of v. Well, that's just negative cosine x. And then du is dx. Hey, that's much better because I can do that, right? So I've got negative x cosine x plus, because I'm going to bring this negative out, cosine x dx, or the integral of that, because I'm going to have to do that. And the integral of cosine is sine, so I've got negative x cosine x minus sine x. And since I'm done integrating, we're going to throw in that extra c, and we're going to be done. That is my integration by parts. All right, one last one, and then we're finished. All right, so let's look at this one. We've got ln of 2x over x squared. And so I am going to, again, to make it a product, I'm going to make it the integral of x to the negative 2 ln of 2x dx. Now again, we want to decide what part is going to be u and what part is going to be dv. Now, again, a good kind of, frame of reference to go by is to make one, or to pick your value that's going to make the derivative is going to be a little bit simpler. All right. So I'm picking the ln of 2x because it's complex and it has a nice easy derivative, and that derivative is simpler. So I'm gonna say my u is ln of 2x, and then the derivative of u will be 1 over 2x times 2, because I still have a chain, times dx, and that means that du is just equal to 1 over x. Then I'm going to let dv be this x to the negative 2 dx, and then do the integral of that, and that'll make v equal to negative x to the negative first power, because I add 1 to the negative 2, that gives me negative 1, and then it'll be negative 2 plus 1, again, give me a negative 1 on the bottom, which gives me the negative there. And so now I have this expression here, and I can say the integral of u dv is going to be equal to, so u dv is going to be equal to uv minus the integral of v du. All right, so we have the ln of 2x, there's my u, times my v, which would be negative x to the negative first, minus the integral of v, which would be just negative x to the negative first du, which we know is just 1 over x, and I suppose I should have a dx there so that I can have a dx there. And so let's simplify this thing. I've got I'll put the negative on the bottom and make this negative ln 2x, like that, over x. And then minus a negative, we'll make that plus. We'll make it the integral of 1 over x squared. Actually, you know what? Instead of that, let's make it, try it one more time. There we go. Oh, son of a gun. All right. This is not going to work. It's going to erase that whole thing. You watch. Yep. Darn it. So we got to say I screwed up and start over. So negative ln of 2x over x minus the integral. I'm going to, and like I said, I'm going to take the negative and combine it with that negatives to make that positive. I'm going to push this x to the bottom. That'll give me 1 over x. I just told you not to do that. Darn it. Yeah, we're gonna say that, what the heck is all this stuff going on? There we go. ln, negative ln 2x over x plus the integral of x to the negative 2 dx. There we go. Now we've got it. Finally, right? ln of 2x over x, and then this thing again becomes, it'll be plus, and so it'll become x to the negative 1 over negative 1. And then since we're done integrating, we'll put the plus c. And so we can finish this up and say that it'll be negative ln of 2x. And since I push this x to the bottom, it'll be minus 1 over x, all plus some constant c. That's a plus. And we will call it like that. Well, that's all I got for you guys today, folks. Fun fact of the Star Wars fun fact of the day is blank. Oh no. Well, it's 21 minutes. I'm sorry. You're just gonna have to wait for another Star Wars fun fact of the day. Um, here's one. It's Star Wars Episode 9, The Last Jedi. Mark Hamill is older than Alec Guinness was in Episode 4, the original Star Wars. There's your good fun fact of the day. Have a great day, folks. I'll see you later. Bye.